Good day, and welcome to Africa TV. My name is Nonkulego Matondo, and this is a STEM Digital School. I hope that everybody is having a great day and ready to do some grade 12 physical sciences. Today is the 10th of July 2020, and we are going to be doing the Doppler effect. Basically, what we're going to be doing today, because yesterday we worked very much on the textbook, I've decided to make a small summary on the what we've done to make sure that everybody understands what is going on with the Doppler effect, and we're going to do some examples. So when it comes to the theory part, I'll probably be moving a little faster because it's stuff that most of them is what we've already done yesterday when we did through the Siavula textbook. But I realized that, it's so difficult to catch on, especially when there's so much work that is done through the textbook. So I try to summarize it and put it all in these slides. And I hope that you guys are ready for a great class. I hope that you guys all have the textbook together. If you don't, if you have some textbooks that are not so reliable, as long as you get yourself some CAPS approved textbooks, they all explain the very same thing in different ways. But obviously, there's other textbooks that give out more information than others. So you can get them on Snaplify. If you do not have the application, you can download the application Snaplify and you can download all your textbooks. Textbooks are free until the 31st of December 2020. So if there's some textbooks that you need, you can get yourself textbooks on Snaplify. And guys, yeah, it's been a great ride. Hey, if you remember, we were doing 2 days ago, we were doing the revision for the work, energy, and power. I hope that everybody is good with the work, energy, and power. And if you do have some problems there, you can send me like a message on my email. It's t33t@gmail.com, and you can let me know. Everything is still the same for grade 12. There has not been any amendments that has been done. All that we've done right now, we are doing term 3 work, which is the work, energy, and power, and the Doppler effect. So those are all parts of the term 3 assessments, okay? As you can see here, there's no amendments that have been done for grade 12, so you do not have to worry. All you have to do is just study everything. But we can do it together. If we work together and go according to the terms, then we can achieve quite a lot, okay? So the Doppler effect with sound, and I'm not sure about homework for today, but like I said today, I wanted to go back and just, get everything in a more compact manner for you guys to be able to understand. So the Doppler effect with sound, we've already explained what the Doppler effect is, and now I want us to go to the first case of a Doppler effect, okay? Okay, so case one is the one of a moving car, a moving source, and a stationary observer, okay? So there's always two cases. So just reminding you that the Doppler effect is an increase or decrease in the frequency of sound, light, or any other wave as the source and observer move towards or away from each other, okay? Remember, guys, that is our definition of the Doppler effect. Is an increase or decrease in frequency of sound, light, or any other waves as the sound and as the source and observer move towards each other or away from each other. So the effect causes a sudden change in pitch, which is noticeable in a passing siren as well as red shifts seen by astronomers, okay? So that's our Doppler effect. So it's all about sound, frequency, and the pitch, but it makes sense. When a person screams, the further away they are, the less the pitch is. But as they draw closer, the frequencies increase and you might hear a much louder sound, okay? So to define this phenomenon, now we've got two cases. We've got the first case where the source is moving and the observer is stationary. And we've got the second case where the source is stationary and the observer is moving, okay? So as you can see here, we've got two people here. This is our source and this is our observer. The source is always the instrument or the mechanism that holds the sound. Okay, so in this case, it will probably be a siren from the car. As you can as you can see, this is a police car. There's probably a siren that's moving there. So as the siren moves closer to this person, it becomes louder. The pitch, the frequency becomes higher, and from this person, it slowly becomes less as it moves away from this observer here. Okay. So the sound waves are represented by concentric circles. Each circle represents a crest or a peak as the wavefront radiates away from the source. So the representation is valid because the wave travels away from the source in all directions. As you can see here, it's away in all directions. Okay, so the representation is valid because the wave travels away from the source in all directions. So the distance between consecutive crests and consecutive troughs in a wave is constant. So you can see here, they're all constant. The waves are constant. Okay, so this figure below, the crests are represented by black lines and the troughs by the orange lines. Okay, so it says here that the sound source is the police car and the middle is the sound source is a police car in the middle and it's stationary, right? Or in this case, it's stationary. It's in the middle and it's stationary. So here, it's still standing still. That's why all the frequencies are all equal amongst each other. All the wavelengths are all equal, right? Because the car is stationary and the people are stationary. The people are the observers or listeners and the car is the source. Okay, so now let's consider the following situation where the source is represented by the black spot right here, as you can see it, and the observer will be here, right? So emits one wave that moves away from the source. The crest represents the wavelength of the sound. So the closer together the crests, the higher the frequency. So if, for example, the sound is going to move that way, you're going to see that the crests are going to become closer to each other. So which means that the pitch is getting louder. But as they widen up, when the person moves away, they widen up. It means that the sound is getting very, very softer. Okay? So here it is. So here is where the crests are getting closer to each other. So which means that the sound is getting louder when the crests are in this manner. So as this crest moves away, the source also moves and then emits more crests. So now the two circles are not concentric anymore. So which means that now the sound that is being given off here is not equal in both sides anymore because now the source is moving towards an observer. Okay, so now the two circles are not concentric anymore, but on the one side, they are closer together. On the other side, they are further apart. So if the source continues moving in the same speed, in the same direction, then the distance between the crests on the right of the source will also be constant, and which means the sound will be much louder. The distance between crests on the left is also constant, but the distance between successive crests on the left is constant, but the larger the distance between successive crests on the right. So you see this one here. You see the crests. They're so far apart from each other, which shows that this source that is standing here is not going to hear crests that are much closer to each other. Okay, so here is a representation. So here's the representation. They say here when a car approaches you, the sound waves that reach you have a shorter wavelength and a higher frequency. You hear a sound with a higher pitch. When the car moves away from you, the sound waves that reach you have a longer wavelength and a lower frequency. You hear a sound with a lower pitch. So it's so sad for this one. The wavelengths are much larger. So from crest to crest, it's a much larger distance, which means the pitch is much lower. But this one, they're very close to each other. Okay. So, and then we have the second case. On the second case, the observer is the one that's moving and the source is stationary. So this car is not moving anyway, but this motorcycle is what's moving towards the car. So while it moves towards the car, and then it's going to pass the car and move away from the car. So to define this phenomena, we sim we similar to case one, also consider a source of sound waves with a constant frequency and amplitude. Two observers are now present, one on the left that will move away from the source, and the one on the right will move towards the source. So there's two cars here. One is moving towards, the other is moving away. Clearly illustrate respective scenario. The crest and troughs are numbered for for it to be easily identifiable on how further away they move from the source, and also makes it easier for them. So this is how it will be, you see. So this is 4, 3, 2, 1. So the observer hears the sound waves emitted by the source and they begin to move. In this case, we ignore the time taken to accelerate. So the frequency of a wave measured by an observer is the number of complete wave cycles per unit time. Okay? Numbering of the crests and troughs assists in identification of complete wave cycles which have been measured by each of the observer at the time, which is the change in time. Okay? So during the elapse of time intervals, the observer moving towards the source experiences the crests and troughs numbered 1 to 5. So they experience these ones from 1 to 5. And the observer moving away from the source encounters smaller portion of the wavefront, crest 3 and trough 4, as you can see there. So the time intervals for each okay? So the observer will interpret the relative motion as per different frequencies measured. Okay. So this is a representation basically that you'll have. So this is how the diagram will look like when it's moving towards and when it's moving away, okay? So now we get to the motion of the observer will alter the frequency of the source measured from a stationary source. So an observer moving towards the source measures a high frequency. The observer moving away from the source measures a lower frequency. It is important to note that we have only studied cases where the sources and the observer are moving directly towards or away from each other. These are the only cases that we will consider for this time, okay? So the formula that provides the relationship between the frequency emitted by the source and the frequency measured by the listener is this one here, okay? So this is the frequency perceived by the observer, which is the listener, and the V, the Fs is the frequency of the source, okay? And then this V here is the speed of the wave. This is the speed of the wave. There will be a constant speed of the wave, okay? And then the VL is the speed of the listener, and the VS is the speed of the source, okay? In the case where the listener is stationary, our VL is going to be 0. And if the source stays stationary, the VS is going to be 0. So if both the listener and the sources are stationary, it means that FL will be equals to Fs. So note that the signs shows whether or not the relative motion of the source and observer is towards each other or away from each other. So when the source moves towards the listener, the Vs is 0. When the source moves away from the listener, the Vs is positive. So when the listener moves towards the source, the VL is positive. When the listener moves away from the source, the VL is negative. So we only deal with one of the source or observer we only deal with one of the source or observer moving in this chapter. So it has to be one, one, one person or one source stationary, or one person or one source moving. Okay. So to understand the sign choice, you can think of about the picture of the motion. Okay. So for the listener observer, we are using the numerator in the equation. A fraction gets larger when the numerator gets larger. So if we expect the frequency to increase, we expect addition in the numerator, right? So a fraction gets larger when the numerator gets larger. So if we expect the frequency to increase, we expect addition in the numerator. If the numerator gets smaller, the fraction gets smaller. So if we expect a frequency to decrease, then it is subtraction in the numerator, okay? Which will be a minus. So this one is for a lesser sound, and this one is for an increase in sound. So for the denominator, the reverse is true because of the fact that we divide by the denominator. The larger the denominator, the smaller the fraction, and vice versa. So if we expect the motion of the source to increase the frequency, we expect subtraction in the denominator, okay? And if we expect the frequency to decrease, we expect addition in the denominator. Okay. Okay. So now we move to the Doppler effect with sound. Here is an example that we can look at. It says here, what is the frequency heard by a person driving at 15 meters per second native 1 towards a factory whilst that towards a factory whistle that is blowing at a frequency of 800 hertz. Assume the speed of the sound in air is 340 meters per second minus 1. So what will this be? This will be our V, the normal V, and this will be our V heard by a person driving. So this is our listener. Okay, this is our VL. Okay, so the question explicitly asks, what frequency will you hear when the observer is moving at a certain speed? This tells you immediately that the question is related to the Doppler shift. The value given in the question are all standard units. So our step is to determine how to approach the problem. Okay, so we know we only have this formula that we're working with. We have our VL, our VS will be 0 because our source is a factory and it's stationary, it does not move. And then the frequency of the source is 800. Then what will be our FL? Our FL, we're going to substitute everything, and this is what we're going to get. But do not forget, guys, when you write your step 4, when you write your final answer, you need to write the driver hears a frequency of 835.29 hertz. That is very important that you write like. But this looks quite simple, doesn't it? I think this example is required. Okay. So moving on, the listener is moving towards the source, so the VL is positive and the source is stationary. Okay, this we've spoken about. So here's another problem that we can do. It says here, for each of the scenario below, say whether the sound that the listener hears will be higher or lower in pitch than the sound from the source. Okay, so it says here, say for each scenario whether the sound that the listener hears will be higher or lower in pitch. Okay, so if the source is moving towards a stationary listener, the pitch will obviously be higher. If the source is moving away from the stationary listener, the source will be lower. If the listener is moving away from the stationary source, it will be lower again. And if the listener is moving towards the stationary source, this one, the pitch will be higher. So number 2, it says, for each of the following scenario, say whether the velocity of the source will be positive, negative, or 0 in the Doppler equation. Okay, so it says here, the source is moving towards the stationary listener. This one is going to be negative. Remember, they've mentioned that when the source is moving towards the listener, Okay. Another one. Okay. So now we say is moving, the listener is moving away from the stationary source. This one will also be negative. Hmm? The listener is moving, the listener is moving away from a stationary source. This one should be negative, right? When the listener is moving away from a stationary source, this one must be negative. This answer here is wrong. And the listener is moving towards a stationary source. This one is positive, okay? So the only time these ones can be negative is if they both stationary. That's when they'll be zero, okay? So you must check. That's why it's important for you guys to understand what you're doing. Because if your answers are wrong, if you don't understand what you're doing, relying on the answers in the book, you will get wrong answers, okay? So number 3, it says for each of the scenarios below, say whether the velocity of the listener will be positive, negative, or zero in the Doppler equation. The source moving towards a stationary listener. The source is moving towards a stationary listener. The Vs will be 0. And the source moving away from a stationary listener, the, the velocity will be 0. And the listener moving away from the stationary source. Oh, yes, indeed. These are the velocities. So, yes, these two are also 0 because these are the velocities, okay? So the listener is moving away from the stationary source. This one will be negative, and the listener moving towards the stationary source, this one will be positive, okay? Okay, thank you guys so much for this little activity. Now we are moving on, okay? Okay, so now we have another problem here. It says here, suppose a bus is heading towards Sean at 1.5 times 10 to the power 8 meters per second, okay? If the bus flashes the headline at Sean, the headline on Sean at a frequency of 4,200 hertz, what is the frequency of light Sean will receive? So given that the observer velocity, in this case, will be seen, the source velocity, Vs, that is 0.5 c, and the frequency V is going to be 4,200. The light frequency received by Sean will be equals to V over 1 plus or minus Vs divided by V, and this is what you will get. So hence the light frequency that Sean obtained is 2,100 hertz, okay? So there's another one here. It says here a car is driven, a driver in a car is traveling on a road next to a railway track. When the train approaches, it blows a horn which generates sound with a single frequency of 420 hertz. The driver is driving at a speed of 18 meters per second and the train speed is 32 meters per second. So further, the sound speed is 340 meters per second. Calculate the frequency of the sound which the driver of the car will hear, okay? So answer, in order to find the frequency, we need to first establish a coordinate system. The positive direction is said to be from the listener to the source. So the source is the horn of the train, and thus the velocity of the train is negative, while the velocity of the driver's car is positive. So the values known to us are V, VL, Vs, and the frequency of the source. So this is how we're going to find our answer, which makes sense, right? So you plot all of them in this equation and you'll find your answer. So once you find your answer of your frequency of the listener, you must make sure that you write, therefore, the frequency of the sound of the train's horn, which the driver will hear, is 488.2 hertz. Okay? So these are the problems, and I hope that you guys understand all of them. This is the Doppler effect. But we're going to do some more application of the Doppler effect. Okay, let's just see this one more example. It says here, a train approaches a station at a constant speed of 20 meters per second with the whistle blown at a frequency of 458. An observer standing on the platform hears a change in pitch as the train approaches him, passes him, and moves away from him. So this one is an exam question from 2011, right? So number one, they ask, name the phenomenon that explains the change in pitch heard by the observer. Number two, calculate the frequency of the sound that the observer hears while the train approaches him. Use the speed of sound in air as 340 meters per second. And how will the observer frequency change as the train passes or moves away from the observer? Write down increase, decrease, or remain the same. And how will the frequency of the observer by the train driver compare to that of the sound wave emitted by the whistle? Write down the greater than, equal to, or less than, and give a reason why. Okay. So the solution for number one, we're going to substitute what we have, right? So the velocity of the listener will be equals to 0, right? It's going to be 0 because the train approaches the station. Okay. So they asked, name the phenomenon that explains the change, right? Oh. Okay. Question one, name the phenomenon that explains the change in pitch heard by the observer. This is definitely what we call the Doppler effect. So if they ask you a phenomena and you're doing Doppler effect questions, you know that it's the Doppler effect. So number two, calculate the frequency of the sound that the observer hears while the train is approaching him. Use a speed of sound of air. So basically, in this case, we have our 340. The source is 20 meters per second, but the velocity of the listener is 0, and our frequency is 458. So this is what we're going to substitute, and this will be our answer, okay? And then now they want to ask, how will the observer frequency change as the train passes and moves away from the observer? Okay, it will decrease, right? Because the train is passing our way. So it means that the sound is also moving our way, okay? So on question 4, they want to know, how will the frequency observed by the train driver compare to that of the sound waves emitted by the whistle? Okay, write down greater than, equal to, or less than. So this one will be equal to because the velocity of the train driver relates to the whistle is 0, or the train driver has the same velocity as the whistle, or there is no relative motion between the source and the observer. Okay. So yeah, this is roughly a 11-mark question. So it's important that you do these questions, okay? So that is all for today. Thank you guys so much for joining me in this classroom. We've done the Doppler effect, and we'll probably be doing the of the Doppler effect on Monday. Thank you guys for joining me here for Physical Sciences Grade 12. This is my email address, tbt.com. If you'd like to ask any further questions and you'd like, and goodbye.